In Chapter 7, we're going to cover a concept known as systems of equations. And a systems of equations is simply a representation of two or more equations and how they relate to each other. We're going to specifically look at linear equations. So we're going to continue on with our work that we did last semesters in chapters 4 and 5 with lines. And we're going to start off by solving a system by graphing. And we're going to look at multiple ways of solving systems and how to determine which method of solving to use as we go through this chapter. So the first thing we're going to look at is by graphing. And so right here we've got a situation that's represented by a systems of equations, and we've got the graph. And so we're going to use this as an example just to kind of get an idea of what a systems of equation is and what it might be used for. So in this particular graph, we're shown the estimated populations of Buffalo, New York and Charlotte, North Carolina. And we want to use this graph to find the year in which the populations of those two areas were the same and what was that population. So if we look at this graph, we see this line right here represents Charlotte and this line right here represents Buffalo. And knowing what we know about lines of graphs, we know that Charlotte is starting at right here 950,000 is right here, so 100 or 1,000 thousands would be 1 million. So in 1990, Charlotte is just under 1 million people, and Buffalo is just under 1.2 million or 1,200,000. The Charlotte population is going up as time goes on. Buffalo is going down a little bit as time goes on. Down here we've got the years since 1990. So this is 1990 right here, 91, 92, 93, and so on. And so to know when they are the same population, we're looking for where these two lines cross. And when we're talking about solving by graphing, we are talking about the point at which the two equations, in this case the two lines, cross. Now this right here is one where from this graph we can't tell exactly what the year and the population were, but we can get a pretty good idea. And so this point right here, if we were to kind of pull down here, this is somewhere between 1995 and 1996 would be the year that they were the same. So it's a little bit closer to 5 than 6. So early, almost to the midway point of 1995. And if we were to go over here to the population, we would be right about here, which is just under 1.2 million. This is 1,150,000. So maybe something like 1,180,000 or something along those lines. And so this example is one where we can't answer these questions exactly, but we can use this graph to get kind of an estimate. Now let's look at one where we can actually use to get an exact answer. So in this particular situation, we are buying juice for a school dance. We bought 15-gallon bottles of apple juice and orange juice, so we have 15 total bottles. The apple juice was $1.50 per gallon, the orange juice was $2 per gallon, and we spent a total of $26. We want to write an algebraic models or equations for this situation and then graph them to tell how many types of each bottle of apple juice we bought. Well, if we look at the way our graph is set up, the x-axis is labeled as bottles of apple juice, and the y-axis is labeled as bottles of orange juice. So that already tells us that our x needs to equal the number of apple juice that we buy, and y needs to represent the number of orange juice that we buy. We know that we bought a total of 15 bottles. We also know about the cost, that apple juice was $1.50 and orange juice was $2, and we spent a total of $26. And so we are going to actually use this information to write two different equations. The first one is going to deal with how many bottles we bought. So x represents the number of apple juice we bought. So that's x. And then we also bought some orange juice, which is the number of orange juice we bought was y. And so if we add the number of, that should be a y, not a j, the number of apple juice plus the number of orange juice, we get our total of 15 bottles. So that's our first equation. Our second equation is going to deal with the cost. We know that apple juice costs $1.50, orange juice $2, and we spent a total of $26. So we've got something equal to 26. That's the amount we spent total. And we know that the total that we spent together can be broken down by how much we spent on apple juice plus how much we spent on orange juice. Well, how much did we spend on apple juice? Well, it cost $1.50 a bottle, and we bought some number of bottles, X. So that is going to be 1.5X. Now, how much did we spend on orange juice? Well, it's $2 a bottle, and we bought Y numbers of bottles of orange juice. So that's going to be 2Y. So these are our two equations. X plus Y equals 15, which represents the total number of bottles we bought. 1.5X plus 2Y equals 26, which represents the amount of money we spent on the juice. And now we need to graph these. Well, we graph these easily by either changing them into slope-intercept form, y equals mx plus b, or we can graph using the x and y intercepts. So this first one, I'm going to use y equals, actually this one would be an easy one to use our either method. Y equals mx plus b, we can just easily subtract the x to the other side. So that gives us y equals negative x plus 15. And so if we were to graph this, our y-intercept is 15. And so that's right here between 14 and 16. And then we're going to go down 1. Our slope is negative 1. So we're going to go down 1 and to the right 1. And so notice we're counting by 2's on each one. So we're going down 1, right 1, down 1, right 1. Like this. Okay? And it is really important in these types of problems that you use a ruler to graph, to draw straight lines, and we want to cover the entire graph because again we're looking for where these two lines are going to cross. Now this one here, we've got 1.5x plus 2y equals 26. So let's go ahead and change that into slope-intercept form as well. That gives us 2y equals negative 1.5x plus 26. And then we divide everything by 2. So that gives us y equals, and negative 1.5 divided by 2. Well, 1.5 is like $1.50. If we divide that in half, that's 75.75 or 3/4. So negative 3/4 x plus 26 divided by 2 is 13. So this one has a y-intercept of 13, and it's going to go down 3 and right 4. So here's 1, 2, 3, 1, 2, 3, 4 is the first point there. And then we go down 3 more. So here's 1, 2, 3, 1, 2, 3, 4. And right there is where they're going to cross. Let's do one more point. 1, 2, 3, 1, 2, 3, 4. And we can draw that line connecting those points. And we see that right here is where it looks like these two lines cross. Well, what point is that? Well, we're in the middle here, which is 7. So it's 7, comma, and over here is 8. So that means we bought 7 apple juice and 8 orange juice. Well, let's check. Does 7 plus 8 equal 15? Yes. And let's double check our, on our other equation, 1.5 times 7 plus 2 times 8 does give us 26.5. So we've got, did I type something wrong there? Okay, so that tells us that we are off just a little bit. So let's take a look and see where we could have made our mistake. And so that's why it's very important to plug those numbers back in or substitute those numbers back in to that equation. And so let's see here. We've got down here, we came down 2, 3. Oh, my lines were a little off. From this point here, we came down 2, 3, and 2, 4 is right here. So let's see if, right here I'm off a little bit on my point. So I'm thinking this one actually might be the right point. So we've got 8, 7. So that would be 8 apple juice and 7 orange juice. Well, 8 plus 7 still equals 15, and let's try this again. 1.5 times 8 plus 2 times 7 equals 26. And so that then is our answer. And so right there, that mistake that I made gives us a couple of things to think about. First of all, it emphasizes how important it is to make sure we draw an accurate graph. Because when I drew this second line, I drew this line above this point rather than right on that point, which threw off where I thought the two lines crossed. The reason I knew that I did that incorrectly was because when I got the answer that I thought it was, I substituted those values back into both of my equations. And so by showing that they worked in both, then I knew that this was correct. Because these two numbers did not work in both, I knew that I had made a mistake. And so that's why it's very important throughout this chapter, especially with the graphing, that you work on checking your answers in both equations. Okay, let's take a look at another one. We're going to do, and we just kind of talked about this concept a little bit, tell whether the ordered pair is a solution of the system and show how we know. Well, we just talked about how the solution of an equation or of a system of equations is a point where both the lines cross. Well, we know that points on a line are solutions of that equation. And so if this particular point is a solution of both equations, then that's where those lines cross. And so what we want to do is take the point and substitute it into both equations. So on this first one, we're going to check it. Remember, this is our x and this is our y. And so we're going to do 4 plus 2 times 1 equals 6. So 4 plus 2 equals 6, and 6 does equal 6. So it works for that one. But we can't just judge from that. We have to go on and check it with the second one. And so that one is going to be 3 times 4 plus 1 equals 11. Well, 3 times 4 is 12 plus 1. Well, 12 plus 1 is 13, and 13 does not equal 11. And so since this point, 4, 1, works for this equation and not this one, that means that this point cannot be where these two lines cross. And so is this a ordered pair a solution? This would be not a solution. Remember, it's not no solution. There is a solution to this system. It's just not this particular point. Well, let's try this one over here. We've got two different equations, another system, and the point negative 2, 1. So let's do the same thing. We're going to do 5 times negative 2 minus 2 times 1 to see if that equals negative 12. Well, this is negative 10 minus 2 equals negative 12. Negative 10 minus 2 is negative 12. And negative 12 does equal negative 12. So that one works. Let's try the other one. Negative 2 plus 3 times 1 equals 1. Well, negative 2 plus 3 equals 1. Negative 2 plus 3 is 1. 1 does equal 1, so it works in that one. Since it works for both, this is a solution. Okay, so this one was not because it only worked for one. It didn't work for both. This one was a solution because it did work in both equations. Okay, so let's look at another graph here, and we're going to see what the solution of this system is. They gave it to us graphed already based on the graph. So these are the two equations that they have graphed for us. And we want to know, what is the solution? Well, as we've seen multiple times already in this lesson, we know that the solution is going to be the point where the two lines cross. And we can see that these two lines are crossing right here. Well, what is this point? Well, this point looks like it's right on those grid lines. So this point would be 3, negative 5. Now we have to be careful, just like in the example with the juice, the point that we thought was where they crossed was not actually where they crossed, it was something different. So we need to check our work. And so this is going to be something that I'm going to be expecting to see in your work when you do your assignment for this section, and as we go through, is checking your work. And so how do we check it? Well, we see if this point works for both of these equations. So the first one is x minus y equals 8. So x is 3 minus y is negative 5 equals 8. So 3 minus negative 5, that's plus a positive. So 8 equals 8, so it works there. And let's try the other one. X plus y equals negative 2, so 3 plus negative 5 should equal negative 2. 3 plus negative 5 is negative 2, which does, of course, equal negative 2. It works there, and so we know that this, because it worked in both equations, that this is our solution of this particular system.